So now we're just going to keep going with this Rankine power cycle. So last time we introduced the Rankine power cycle. And it looked like this. So this is for the ideal Rankine power cycle. Okay, so remember, just jogging your memories, what goes on the vertical axis of this graph that we used?
Temperature.
Yep. And on the horizontal?
Entropy.
Yep, perfect. Specific entropy. And our state one, anyone remember where our state one fell on this? I mean, this is a lot. Yes. Remember what phase is this in?
Saturated vapor.
Perfect. Nice work. So this,
It's a diagram. I remember pictures.
okay, so state one is there. From state one to state two, what is that process?
Temp drops.
Yep. So, yep, it goes straight down. Do you remember what?
You're on a roll.
You are on a roll. That's awesome. So this is state two. Do you remember what is the device that we're going through from 1 to 2? That's right. That's a so this is an isentropic turbine. And then from 2 to 3, where does 3 end up? Saturated liquid. And what's this device?
The condenser.
It's the condenser, yep. And what do we know about that process? We always switch off. There's only isobaric. Perfect. And then we're at state 3. And now where do we go to state 4?
You pump it up.
Pump it up.
Up the jam.
Yeah, to about there. So that's our state 4.
We throw heat into it.
And what is this? What is this guy?
Isentropic.
Correct? So they alternate isentropic and isobaric. And what is this? Oh, pump. That's what you said, yeah. And now the next from 4 to 1 happens in sort of 2 segments.
Heat it up
First, you have to get it to the saturated liquid, and then you have to turn it into a saturated vapor. And this is the kind of the key step. This is it is isobaric.
I'm just seeing a guy shoveling coal.
Yeah, exactly. So boiler. Yep,
Boiler.
exactly. Perfect. That's great.
And
and-
put guys shoveling coal in the test.
Yeah, sure.
Okay.
Yeah, I'm sure. That's fine. And what we learned from examining this is that the ideal efficiency of a power cycle is 1 minus TC over TH. You can put the over bars over it to show that that's just some place on the boundary, or you can assume that it's all the same temperature and just do this. So now what we're going to do is we're going to express the efficiency in terms of enthalpies, specific enthalpies. And these are going to be useful for our calculations. And we're going to do this by using the first law for control volumes at each one of these. Okay, so from state 1 to 2, this is the isentropic. And by the way, so this memory jog thing, like, I think it'll be helpful. You'll be happy if every time, like, just slow down as you do these and ask yourself, like, what's the phase here? What type of process are we doing going from here to here? You know, just ask yourself that stuff each time you do it until it is kind of natural, you know. It helps a lot. So from state 1 to state 2, we have the isentropic turbine. This is where we benefit from this power cycle. This is the work that's coming out. Okay, so I'm going to start each one of these with the full control volume first law, and then we're going to cancel stuff like we have been a lot. So we're going to start with d dt for the control volume is equal to q dot minus w dot plus mi dot times the quantity hi plus vi squared over 2 plus gzi minus me dot times he plus ve squared over 2 plus gze. We're going to assume this is steady state. We're going to assume that there's no heat transfer. And we're going to assume there's no significant change in kinetic energy and no significant change in potential energy. So d dt is 0, q dot is 0, mi equals me dot, and then those go away. And so we have from this that w dot for the control volume is equal to m dot times the quantity h inlet minus h exit. Okay. And now we're going to think about what all this stuff is. So this w dot is the work done by the turbine. Since we're coming from the first law, all of our sign, our sign convention that we're using in both of these two equations is the first law sign convention. So now we have to think, okay, the work coming out of the turbine is possible, the work at the turbine is positive when it's coming out. This is our WT dot. And so that sign convention matches the sign convention for the first law. So I'm just going to replace this with WT dot. At the pump, you can imagine it's going to be the opposite, because the work that we expect that we're going to call positive at the pump, WP dot, is coming into the system. Okay, but so we have WT dot is equal to M dot times, and now let's think about what the inlet and the exit are. The enthalpy at the inlet is the state 1 enthalpy. At the exit is the state 2 enthalpy. And so our final form is, we can write this as W dot at the turbine divided by the mass flow rate is equal to H1 minus H2. Any questions about that one? So now we're going to the second process. So this process goes from state 2 to state 3. This is an isobaric condenser. We know that you can't have a power cycle without losing heat in the form of exhaust, and this is where that happens. So I'm going to start with the full form again. dE dt is equal to Q dot minus W dot plus Mi dot times the quantity Hi plus Vi squared over 2 plus Gzi minus Me dot times the quantity He plus Ve squared over 2 plus Gze. And we're going to assume that this is steady state. We're going to assume that, so this condenser is just a rigid walled container. There's no power coming in or out, so we're going to assume that W dot is equal to 0. And we're going to assume there's no change in kinetic energy and no change in potential energy. So we can cancel the EDT. We can cancel W dot. We just have a single mass flow rate. And we can cancel the potential and kinetic energy terms. And so we get that QCV dot is equal to, now notice I'm just doing the algebra here. I mean, just spot what I'm doing here. Our QCV, I guess I'm switching sides, you can think of. So our QCV is equal to M dot times, this time, HE minus HI. And now let's think about what the heat is doing. So the heat at the condenser is our QC dot. Okay, our QC dot, do we call that positive going out or positive coming in? So right now we have it in the first law of sign convention, but like thinking about the direction that we know things are going to happen in a condenser, is heat going in or out of the system? Going out. So yeah, so what we have is negative Q dot at the, so C for cold or condenser, and that's equal to M dot, and our H at the exit is H at state 3. Our H at the inlet is H2. And so now, I guess you could think of switching the sides again of the equation, and you get that QC dot over M dot is equal to H2 minus H3. Any questions about that? Okay, now we're going from state 3 to state 4. This is an isentropic pump. And so start with the full form, dE dt is equal to Q dot minus W dot plus Mi dot times the quantity Hi plus Vi squared over 2 plus Gzi minus Me dot times the quantity He plus Ve squared over 2 plus Gze. And we're going to assume this is steady state. We're going to assume that Q dot is 0 and that there's no significant change in potential energy or kinetic energy. So dE dt is 0. Q dot is 0. The mass flow rates are the same. Cancel the last two terms in each pair of parentheses. And now, simplified, we can write this as W dot for the control volume is equal to M dot times the quantity Hi minus He. At the pump, does the work we expect, so at the pump we expect work to be done on the system. So is that, so negative, exactly. So, so we have negative W dot at the pump is equal to M dot times the quantity. H at the inlet is H3. H at the exit is H4. And so you can flip the signs and you get WP dot over M dot is equal to H4 minus H3. Now there's one simplification that we're going to use probably most of the time on this, maybe not always. So one thing we'll use, let's say usually for this pump, is that, look at this diagram. What's the phase of the working fluid as it goes from state 3 to state 4? it's liquid, and so we're going to assume that this is incompressible. And so we're going to assume that the specific volume at state 4 is equal to the specific volume at state 3. And we're going to use the TDS equations to re-express H4 minus H3. Okay, and you can think of H4 minus H3 as the change in specific enthalpy over this process. So TDS is equal to, the one we're going to use is dH minus VDP. Is the pump isobaric or isentropic?
Tropic.
Yep, right. So isentropic means that this goes to 0. And so we have that 0 is equal to dH minus VDP. Or in other words, dH is equal to VDP. And that means we can integrate both sides. And so we get that the change in specific enthalpy is equal to this integral. But notice that, V is constant over this whole process, so we can pull this out of the integral. So this V is constant because it's incompressible. And so that lets us write, so imagine pulling the V out of the integral and then take the integral, and you get that delta H is equal to V delta P. So in other words, H4 minus H3, which is our expression for WP dot over M dot, is equal to the specific volume times the pressure at state 4 minus the pressure at state 3. So when you get to the pump, just remember that you have these two different ways to represent this W dot, or to represent H4 minus H3. Depending on just what values you're given, one might be easier to figure out than the other one. And then our last one, so this was state 3 to state 4. Now we're going from state 4 to state 1. And this is the isobaric boiler. And so one more time, start with the full thing. So we have d dt is equal to Q dot minus W dot plus Mi dot times the quantity Hi plus Vi squared over 2 plus Gzi minus Me dot times the quantity He plus Ve squared over 2 plus Gze. And we're going to assume this is steady state. The boiler, is that going to have, so in each of these, we've had either the rate of heat transfer, the rate of work transfer equal to 0. Which one is it going to be for the boiler? Work, right? So W dot is equal to 0. And change in potential energy is 0. Change in kinetic energy is 0. So dE dt is 0. W dot is 0. The mass flow rates are the same. Cancel the second and third terms in each set of parentheses. And you get 0 is equal to Q dot for the control volume plus M dot times the quantity Hi minus He. And so we can write this as Q dot for the control volume is equal to, I guess I'll go negative M dot times the quantity Hi minus He. Do we expect, so this is the first law of sign convention. Does that agree with the direction of heat flow at the boiler? Yeah. So I'll write this as Q dot at the boiler is equal to M dot at He times He minus Hi. And so Q dot at the boiler divided by M dot is equal to H1 minus H4. Okay, so the thing to remember here is that at each step, we had to think about whether the direction of Q dot or W dot agreed with the first law of sign convention. Okay, so now we did all this to express the efficiency in terms of enthalpies. So now we're going to express eta in terms of these state enthalpies, these specific enthalpies. So we're going to define the efficiency as, so remember going back to the definition of efficiency, think of it as the thing you're trying to produce divided by the cost of this energy you're producing. Well, what we're trying to produce is W dot at the turbine minus what we lose for powering the pump. So that's the net work that we get out of this power cycle. Divided by the cost, which is the heat transferred at the boiler. And notice that without changing anything, we can multiply and divide, everything by m dot and write this exact same thing as WT dot over m dot minus WP dot over m dot divided by Q dot at the boiler over m dot. And now we can just plug in our values, our expressions that we got from that whole analysis. So eta is equal to, we have H1 minus H2 minus the quantity H4 minus H3 divided by H1 minus H4. And you can get rid of those parentheses. You have H1 minus H2 minus H4 plus H3 divided by H1 minus H4. And then just rearrange. So now you can write this as H1 minus H4. I'll put those in parentheses. Minus H2 minus H3. All over H1 minus H4. And then in its final simplified form, you can write this as, so H1 minus H4 over H1 minus H4 is 1 minus H2 minus H3 divided by H1 minus H4. And the numerator of this fraction and the denominator are both positive. Okay, so a couple of things so last time we learned, now we know that the efficiency is equal to 1 minus TC over TH. And we also know that this efficiency we can write as 1 minus H2 minus H3 over H1 minus H4. So what does this tell us? This first one tells us that our power cycle is more efficient as the boiler temperature, the high temperature, goes up or the condenser temperature goes down. And this second one tells us that our cycle is more efficient as the pressure in the condenser goes down or the pressure in the boiler goes up. So remember, those are important practical facts that we've figured out from this. One other thing that we want is, so the back work rate. So back, I'll call it BWR, is equal to the rate of work done to power the pump divided by the rate of work gained at the turbine. And of course, you want this small. It's no good to build a turbine and then spend all the energy you gain just powering the pump. Any questions about that? Okay, that's it for today.